Tierney here from Monroe Community College, and in this video we're going to talk about the basis of Bohr's atomic model. He used something called an emission spectra to help him come up with this theoretical model. In order to understand what an emission spectrum is, we need to understand what a continuous spectrum is. I'm sure you've seen this before if you have some sort of prism hanging in a window and you see a rainbow that appears. What's happening is that the prism takes that sunlight and separates it out into its different wavelengths. It's called a continuous spectrum because you see all the different colors that make up that spectrum, which is a wide variety. It has a whole range of colors that are in that spectrum, and therefore it has a whole range of wavelengths. Now, the spectrum, if you recall, Roy G. Biv, is red, orange, yellow, green, blue, indigo, violet. And so this is given whenever you separate the wavelengths of either the sunlight or a white light source. An emission spectrum is something different. You get an emission spectrum when you have an element in its gaseous form in a tube, and we add energy to it, often in the form of electricity. This produces a light. But when we separate it out into its wavelengths with a spectrometer, we see that we don't get a continuous spectrum. In fact, we get lines on the spectrum, which means we only get specific wavelengths that are represented within that light. So this is a picture of the hydrogen spectrum. Notice that there are just fine lines that are represented. So Niels Bohr took this phenomenon and he wanted to use this to help explain how electrons exist in the atom. Now, I don't know about you, but I think this is amazingly clever that he was able to think that this fine lines of wavelength has anything to do with electrons. And in fact, it does. So here's the principles of Bohr's model of the hydrogen atom, and we're going to look in a little bit to see how he was able to get this from the emission spectrum. So his first principle is that only photons of specific wavelength, lambda, are emitted, and this electron energy is called quantized. Quantized means that its only specific values are allowed. It's not continuous. Continuous and quantized are opposites of each other. The second principle is that an electron can exist in quantized or fixed orbits called stationary states. We denote this with a lowercase n. In moving from one stationary state to another, an electron absorbs or emits a photon whose energy corresponds to the difference in energy between the two states. This is only valid for one electron species. The most common of those is hydrogen. This is why it's called Bohr's model of the hydrogen atom. Right now we can already see the limitations of this model, but it is a very useful model. The other two common species that just have one electron are helium plus and lithium 2+. So let's take a look at the terms that you need to know in order to understand what is going on here. So an electron is normally found at its ground state. The electron occupies the lowest possible energy level, or as the last slide called it, the lowest possible stationary state, which is denoted by n equals 1. The numbers go up as whole numbers, so the next highest energy level would be n equals 2. Absorption happens when that electron acquires energy, usually from electricity, and it's able to jump to a higher energy level called an excited state. Much like when we have an energy bar, we get a higher energy level. Electrons also, when they get energy, they jump up to a higher energy level called that excited state. Emission occurs when that electron eventually jumps from its higher energy level down to a lower energy level. So just like with us and our energy bar, as you're doing all your exercise, eventually you're going to get kind of pooped out and have to go back down to the couch. Same with the electrons. They're not stable at the excited state, and they will eventually go back down to their lower energy level. When they go down to the energy level, the lower energy level, they give off that extra energy, and it's in the form of light. And this light is seen as a line in the emission spectrum. Let's take a look at what this looks like. So here is our hydrogen atom. It has one electron in the n equals 1 level. When it gains energy in the form of electricity, that electron then goes up to a higher energy level because it has absorbed that energy. It stays in this excited state for a short time but is unstable, so it needs to jump back down to its ground state, and when it does, it gives off energy in the form of light. Now that energy is represented in the spectrum because each difference between energy levels has its own unique amount of energy associated. So when we look at the jump between n equals 3 and n equals 2, we see that it gives us a red line at 657 nanometers. If you recall, energy and wavelengths are inversely related, so a higher wavelength means a lower amount of energy. If you notice the drop from n equals 5 to n equals 2, this is a greater difference of energy. And if you notice, the wavelength at 434 nanometers violet is smaller. So indeed, this bigger gap of energy gives it a smaller wavelength, whereas the smaller gap of energy gives it a bigger wavelength. We're going to look at specific amounts of energy and how they relate to this in our next video. There is another video in this series, and you need to watch that before we discuss this in class.